Log on, tune in, find out. Another good idea from Cambridge.
So let me recall where we stopped yesterday. So we had our finite group of Lie type, an algebraically closed field, whose characteristic is either 0 or a prime L, which is not the prime of definition of this group. And we saw that the set of irreducible representations of G could be partitioned into pieces and indexed by such pairs where, so L is a Levy subgroup, X was a cuspidal representation of L, and then we denoted these pieces by this notation. So this here was defined as the set of all irreducible representations of G, which well, there were several ways to express this. We could say Y is a submodule, or equivalently a factor module of this Harish-Chandra induction. And then we saw, using this theory, this theorem on Hom functors, that actually this set is in bijection with another set of irreducible representations, namely with this endomorphism algebra. Yeah, and this is what we would call a Hecke algebra. So hence the problem of trying to understand the irreducible representations of these algebras. So I mentioned already a little bit about the structure of this algebra. Let's recall that also. So what was relevant was this inertia group. So that's the stabilizer of X in this normalizer quotient. And I didn't say this yesterday, but the first step here to see why this algebra is related to this group is the following result. And this I leave as an exercise. So using the Mackey formula for this Harish-Chandra induction and restriction plus Frobenius reciprocity, plus the definition of cuspidal. So you get a 3 or 4 line proof that actually this endomorphism ring so how do you start to use Mackey formula and Frobenius reciprocity here? So this is Hom Kg RLG X RLG X, and then you use Frobenius reciprocity to move down to KL, and then you use the Mackey formula to decompose the space. So this I leave as an exercise, but what you find is that this has dimension the order of this group. So this is a first indication that this algebra has something to do with this group. In fact, already from this, if you follow all these isomorphisms involved in the Mackey formula and the Frobenius reciprocity, you actually get a standard basis indexed by the elements of W. Get standard basis, which we will then call TW. And when you then work a little harder to try to see how these basis elements multiply, you get a presentation of this algebra in terms of these generators and relations. So I don't want to write this down in this complete generality. It is possible, but it is technically a little bit heavy, and I would just spend 20 minutes in introducing notation. So I will just do this in this one special case, which is the most best known anyway. Namely, when this pair here, Lx, is the simplest possible pair that you can think of. Namely, so remember L was a levy in some parabolic. So if you choose as parabolic simply the Borel subgroup, and as the levy it's maximal torus. So if we take here T, and then as caspital representation here, just the trivial representation of T. So we write B as U times T. And this is the trivial representation here. You see the this WLX then is just the while group of my finite group. Is just W. And in this case then so we know that W is a Coxeter group. So it has a presentation like this. And then so it is possible to write down in a nice way how these basis elements multiply, and this is in this special case due to Iwahori and Matsumoto in the 1960s already. So the multiplication of the standard basis of this algebra, so let's call it H and K, G, R, D, G, is given by so first of all for W in W, write W a reduced expression, then the TWs multiply accordingly. So it's enough to understand how such a TS multiplies to a TW. So then for W in W and S in S, we have TS, TW. P as W if the length goes up, and it's Q CS. So the image of this in K so we have these quadratic relations if the length goes down. Yeah, so this completely determines the structure of this algebra, and this is, I just forgot it to say it, yeah, where so these numbers, so CS is a positive integer, and it's defined by the condition that if you take the Brouwer decomposition, so you look at the Brouwer cell corresponding to this generator in your group, and you see that the cardinality of this set is a power of Q, and this is this exponent here. Yeah? So if your group is a finite Chevalier group of split type, then all these CS's are equal to 1. But if you have groups of non-split type, then they can be really different. So if G is of split type, e.g. G is GLN FQ, then all these are 1. So let me just give you an example where you can really see that they can be different also. Example of non-split type. Well, we have the finite unitary groups. So how do you get them? You can start again with GLN over an algebraic closure of FQ, but you have to take another Frobenius map, not this standard one that I mentioned where you just raise coefficients to the qth power. If you twist this Frobenius map a little bit, you get another finite group inside there, and this is the finite unitary group. And this here has, as a group with the Bn pair, it has while group. Of type B, where M is n minus 1 over 2 if, is this correct? Yeah, if n is odd, and n is even. And then the parameters here are, so here you have Q squared, so all these CS's are 2, and here you have another one where C is 1 or 3 according to, so if n is even, and here if n is odd. So here you really have two different parameters. Okay. Yes, yes, yes.
Manas, can you just say again, what is the stabilizer of X in MGL?
That's the definition of this double.
What does it mean? What's the
So
stabilizer?
X is a representation of L. Well, the normalizer acts on the irreducible representations of L.
Yeah.
So you take the stabilizer of this X in this.
So things that fix the whole representation.
Yes. Okay, so this is this special, important special case where the structure of this endomorphism ring can be described in this simple way. In the general case, as I said, so there are a number of complications that arise. First of all, in general, this group is not just a Coxeter group. It usually has a large subgroup, which is a reflection group, and then there's a group on top acting on it. So you have some semi-direct product structure. This is also reflected then in the structure of this algebra here. It's a kind of semi-direct product. But as I say, then the relations become a bit more complicated. So I just don't want to introduce all this notation. But the spirit is somehow the same.
Can I ask, this is
Yeah?
a case I'm slightly confused about. The root spaces in this unitary group form a BCN root system, is that true, or is that?
Yeah, as a finite group with a Bn pair, the Weil group of this Bn pair is of type Bm.
No, I'm asking about if I take the roots, the U alphas, the UA, inside this Chevalier group.
Yes.
Do they form a non-reduced root system? Or is it still a reduced root system?
Depends on the parity.
Well, how do you define the root system there? You say the U alphas. This is just a collection of subgroups, and this, I mean.
The roots with respect to the maximal split torus makes sense.
Okay, yeah. And this is.
And you get a root system, and it's sometimes non-reduced and sometimes reduced, depending on the parity.
All right.
Yeah,
That's
okay,
fine.
yeah. So one important observation coming from this structure result is that, so this is that the structure constants of this algebra H, so let's stick to this special case here, of H, are given by polynomials in Q, or more precisely, so I can write Tx, Ty, the product of any two basis elements in this algebra, in this form where these G's are integer polynomials independent of P and Q. Yeah? Well, you could, here I wrote down what these polynomials are in this special case of this product here, and of course then if you take an arbitrary element here, you would get more complicated formulas there. So this observation then makes it possible to define a generic algebra. You would call it generic algebra. So let's call it H. So where A we take as base ring, a ring of Laurent polynomials. H is free as an A module with the basis indexed by W, and the multiplication is given by simply I use these polynomials, not the evaluated polynomials, but the polynomials as such as structure constants for this algebra. And for reasons that will become clear a little later, I artificially take this v as a kind of square root of this parameter here. Or explicitly, so you have Ts, Tw, here is Sw if the length goes up. And this relation if the length goes down. So we have now this new algebra over this more complicated ground ring, the ring of Laurent polynomials, and the structure constants are polynomials. And the point about this constructions is, of course, that here you have one object to study and you get all the others by specialization. So consider ring homomorphism. So from this ring of Laurent polynomials, we have this homomorphism which sends the indeterminate to a square root of q in K, and then this algebra, the endomorphism ring, is just the extension of scalars from this generic object to K. So in this way, this is the conclusion of this discussion. Hence, so study one object, this H, this generic thing here, and representations of such specialized algebras for various theta A into K, where K is a field. Yeah. So once we have arrived here, you can somehow forget for a moment at least this background coming from groups of Lie type and interpretations as endomorphism algebras of something. We can just deal now with such generic algebras associated to finite Coxeter groups. And we want to understand how the representation theory of these algebras looks like. So I mentioned already last time that in some cases when everything is semi-simple, that there is a nice result that the representations of such an algebra are just in bijection with the irreducible representations of the underlying group W. So this is true when everything is semi-simple. So we also have to, or we want to deal with the fact, with a case where we are in the non-semi-simple situation. So how do we go about this? Now, of course, if these algebras were just any kind of associative algebras, then we could not hope to get some nice theory for studying the representations. But as it turns out, these are quite special types of algebras, and the convenient framework for studying their representations is that of the theory of cellular algebras of Graham and Lehrer. So I recall what this means. I think this will be useful for some other talks in these 2 weeks as well. So Graham and Lehrer, they defined a class of associative algebras which they called cellular algebras. And these algebras have a very nice representation theory. So general definition. Well, but I still use the same letters here, so let H be an associative algebra. Over an integral domain A. So we assume that H is finitely generated and free over A. Now, to define what it means for H to be a cellular algebra, this amounts to specifying a basis with nice multiplicative properties. So, and this is done in terms of, Graham and Lehrer do this in terms what they call a cell datum for H. So this is a quadruple lambda m c star where. So now we have some axioms. So lambda is a finite set endowed with a partial order then this M actually stands for collection of finite sets indexed by the elements of lambda. And that's the first statement now. So this C then stands for a basis of H. Namely, the first axiom is that actually we have we can label a basis of H by these data here. So is an A basis of H. Yeah? That's the first statement. I just have a conveniently indexed basis of H. And now the other axioms, the real axioms that impose some conditions, say something about how these basis elements multiply together. So the first thing is the star thing here. So star is an anti-involution. So just a an anti-homomorphism of order 2, such that if I apply it to such a basis element, the effect will be of swapping these two indices below. Yeah. So that's also maybe not such a spectacular condition. So now is the third one. So let's take such a basis element and multiply it from the left with some element of H. Now, we said that these C lambda ST form a basis, so I can expand this product in this basis. And this third condition, now the most serious one, tells us something, essentially says that many terms in this expansion should be zero. Namely, first let's look in this expansion at those basis vectors which have the same lambda here. So then it says, and we write this like this. So this is just the beginning of the expansion. And then the point is that all other terms in this product expansion will be C mu's and UV, C mu's, where mu is strictly smaller in this order than lambda, plus a linear combination of terms C mu U V, where mu is strictly smaller than lambda. So there are actually several statements here in this condition. So first of all, note that I only let run the first index here, the S prime. Yeah, a priori, I should also expect terms where the second component could occur here. This is the first statement, so that here only the fixed component is fixed. The second component is fixed. Then the next statement is I did not include the T in the notation of this, and this is actually a statement so that this thing here does not depend on the second component. So these are very restrictive conditions on the multiplication in this algebra. So you see, for example, so in particular, if you define these sets, a given a fixed lambda, and then let's define this set to be the span of all C mu, where mu is in lambda, mu less than or equal to the given lambda, and uv runs over all m in mu. So just the A span of this actually turns out to be a two-sided ideal in H. Yeah, left ideal is clear from this condition. Here I multiply from the left and I see in the product there are only terms with mu's which are smaller. So that's clear, it's a left ideal. And the fact that it's also a right ideal follows from this condition, that the star here. So using the star thing, every left-handed rule has a right-handed analog. So and in fact, yeah, this is the essence of this. So the basis, this basis of H is adapted to the left, right, and two-sided ideal structure of H. And one other important issue is also that we definitely don't want from the start to work with an algebra over a field. We want to have this flexibility to work over a ring, so that we have this possibility of doing such specialization somewhere else. Yeah? For example, if we allowed well, a field, then using Wedderburn or other theorems, I mean, you would easily get bases adapted to ideal structure in your algebra. The point here is to do this over this ground ring A. everything is defined over A. It's an important condition here. So why does this existence of a good basis lead to some nice representation theory? So this can now also be explained. So given lambda in lambda, let W lambda be a free A module with basis indexed by the elements of M lambda. So this is just as an A module, but using these structure constants, we can define an action of H. So there is a left action of H. So namely, I just have to say how an element of H acts on such a basis element. Well, and there I simply use these RH as S primes. And you will immediately check or easily check that this defines a left action of H on this thing. Then next.
Is S prime to come before S? Or
Sorry?
is S prime supposed to come before S?
I think so, yes, yes. Is it? And it should also come before. Then next, each of these W lambdas carries a bilinear form, a natural bilinear form. Which is defined as follows. So I have to say what this product should be. And this is again an element of A, which is such a structure constant, and it's the following. It's R, H, S, comma S, where H is this basis element. So you take an S, you take a T in M lambda, and then you look at this H and you take this structure constant. And what you then check is you have an invariance property, then G lambda H dot CS CT is the same as G lambda CS H star, this anti-involution dot CT. So you have some invariant bilinear form on these modules. Well, the proofs of this are simple verification. I wrote down some formulas here, and you have to check these formulas using these defining equations. Yeah? These are structure constants of an associative algebra. So you have some identities between these structure constants, and they give you these properties. So, and once you have this, we can do the following. So now let's go to a field. So let theta be a ring homomorphism into a field K. Then we get HK. an associative algebra over a field. And since all these other ingredients are defined over A, by extension of scalars, they pass on to this algebra here. So we get a basis, if you like, tensor 1. Is a basis of Hk, which has these nice properties there. Also, we have now these are representations for Hk. And we have a bilinear form on these modules here, which satisfies this invariance property here. Now, in general, these W lambda k will not be irreducible, but we have this bilinear form, and this invariance implies, so invariance of implies that the radical of this form is an Hk submodule of W k lambda. Yeah, as you check immediately, if you have an element in this module which is orthogonal to everybody else, then the image of such an element under H will also be orthogonal to anything else using this invariance property. So you get this, so you can define L lambda to be these radical quotients, and then the theorem, or one of the theorems proved by Howlett and Lehrer is not Howlett and Lehrer, Graham and Lehrer, that the irreducible representations of this specialized algebra Hk are just given by these L lambdas. Well, it could happen that this form here is completely zero on your module, then the radical is everything, and this quotient is zero. So, but if I take, so let's introduce this notation. So if I just take those lambda such that this form does not completely vanish, so that means then this radical will be a proper submodule of this, so these are non-zero modules, and what they prove is that really these non-zero ones are irreducible, and you get all irreducibles in this way. So this is one reason why these cellular algebras are important. You get automatically with them a nice classification of the irreducible representation for every specialization of this algebra. Yeah? So you have your one.
Different lambdas, for different lambdas, modules are not reservoir.
No, you really get different ones. Yeah. Okay, so that's this general framework for studying representations of an associative algebra, but of course we have to see if we can find such a basis in any given algebra that we wish to study. And this is the point. As it turns out, we can always find such cell data in these Hecke algebras. So let me just some 15 minutes, so I can just give some special case here. First historically the first case where this was known. So back to generic Hecke algebras. So we assume that our H is such an algebra. Can we find a cellular basis in there? We have a standard basis, so we have the standard basis here, and this definitely is not a cellular basis. I mean, first of all, you would have to relabel it in a nice way, but you see all these TWs are invertible in H, so they will not be adapted to any nice ideal structure in your algebra. But there is a much better algebra, much better basis in H, and this is the Cascanostic basis. So let me introduce this. So first define TS. Tilde, we just renormalize this basis a little bit, and then TW tilde. If W is a reduced expression. So we just have this basis here. Yeah, but as I say, it's just convenient to renormalize this a little bit. It's not a big changement. So to get the Cascanostic basis, we need a ring involution on H. And this is why it's convenient to introduce this basis. So let's take a typical element of our algebra, and I want to define this Cascanostic bar involution. So this should be a ring homomorphism of order 2. So what can I do? I do something to the coefficients. So each coefficient here is a Laurent polynomial in V, and what I do is simply I replace V by its inverse. So it's not A linear. And then I do something to these basis vectors, namely I invert the index, and then I invert the whole basis elements. From the quadratic relations, you can easily check that all these TWs are invertible in H. So this is a ring involution. And then Castan and Lustig saw that there is a canonical basis fixed by this involution. So this is so in this first article, which just dealt with the fact when all these CS are equal to 1, and then soon afterwards Lustig extended this to all possible choices of such parameters. So the statement is for each W in W, there is a unique CW in H such that CW is fixed by this involution, but this doesn't make it unique. You have to say something about the expansion of this element in terms of the old basis. So this is the second condition. And now there are always two versions of this Castan-Lustig basis. One is the unprimed and the C-prime basis. So you always have to say which one you prefer. So I use this convention here, which is really the C basis. So you say that in the expansion here, this basis element occurs with a sign, and all the other basis elements occur with coefficients which are Laurent polynomials which don't contain a constant term or negative power. So with these two conditions, you can show that there is a unique such CW, and in fact these
The y's should be less than or equal to w?
it will follow from this. You can omit this Brouwer order condition from the definition. So this is a new basis of H. Now, it would be fantastic if I could just add another theorem and say, well, you have to introduce this lambda and m lambdas, relabel these CWs in terms of lambdas and STs, and this gives a cellular basis, but this is not true. So it's only true in one example, and this is actually was apparently the model for the definition of Graham and Lehrer. So let's look at the case where W is the symmetric group and all these CS's are 1. Then I want to state that this basis is a cellular basis. Yeah, but I have to get this lambda, and I have to label my basis. Well, is it written somewhere? They have to be labeled as C lambda ST. So what is the lambda ST corresponding to a W in Sn? Well, and this is given by the Robinson-Shenstedt correspondence. So what does this give? Most of you maybe have seen this. So you can associate to each partition of to each permutation of 1 up to n a pair of standard tableau, so ST are standard tableau of the same shape. So you have that's a Young diagram, and tableau is you have to fill these boxes by numbers, and standard tableau means from left to right and from top to bottom these numbers have to be increasing. So for each permutation you can construct such a pair of tableau. Now I don't have the time, so if you haven't seen this, we can do an example this afternoon. So if we write this a bit more differently, so the shape of such a tableau is just a partition of n. So this actually means, so here we get a bijection between Sn and this disjoint union of such things, where this here means T lambda I denote the set of standard tableau of shape lambda. So, and there are, maybe we see the ingredients that we need for our cellular basis. Yeah? So we can take, let's take lambda, capital lambda, the set of all partitions of n. We take m lambda to be the set of standard lambda tableau. So what else do we need? We need a partial order on lambda. There is a natural partial order on the set of partitions given by the dominance order. We need the star thing there is a natural star anti-involution in every Hecke algebra. Simply by inverting the index of such a basis element. This works for any Hecke algebra. And then if I define C lambda st to be the Cascanostic basis element CW, where W under this correspondence corresponds to the pair of standard tableau ST here. Under the Robinson-Schinstedt correspondence. And then the statement is that this quadruple is a cell datum for H. Yeah. So this was already in the original article of Graham and Lehrer. I should maybe say one final word about the proof. So I didn't give many proofs here, but so this whole general theory of Graham and Lehrer, well, it's tricky, but it's elementary. It takes some 10 pages or so to prove this result, for example. You have to do manipulations with your basis and your axioms. Also, this theorem here is elementary. Castan and Lustig, they construct these CWs by induction on the length of the length of W. You get even some recursive formulas for that. This Robinson-Schinstedt correspondence business has long been known to combinatorists. But, so all the ingredients here, everything is elementary, but in order to prove these multiplication rules, there are some tricky things involved, and I think so there you really need some rather subtle properties of the multiplication of this Castan-Lustig basis. Yeah? So this is not so obvious how this goes, but at least for the symmetric group, you get this smooth picture here. What I want to do then tomorrow is to say how you can extend this result to other types of Coxeter groups and Hecke algebras, and also come to finally to what my title was saying, namely Hecke algebras at roots of unity. Yeah, so we will see some applications to representation theory of these algebras and the underlying algebraic groups. Okay.
Are there any questions? All right. Again, well, it's lunch now, and we resume again at 2 o'clock. Thank you, again.